Welcome to another class of linear programming. We have been talking about duality, and as we know, in case of linear programming, strong duality exists. What it means is, except these small boundary cases when one could be feasible, unfeasible, one could be unbounded or something, if both have a feasible solution, then their values agree. Not just that, we have this very nice connection between the constraints here and variables there, and the variables here and the constraints here. Right? And we have seen how to take dual using primal and all these things. Now the focus would be to give you nice application, simple, obvious, kind of straightforward applications of strong duality. Okay? One of the very nice application is Minimax theorem. This was given by von Neumann, and if you don't know him, then time to increase your general knowledge. Go home, search in Wikipedia, inferential figure in computer science, and I think in somewhere in 1940s, he gave this Minimax theorem, which we are going to talk about, and it's a straightforward application of strong duality, and it's generally considered in the field of algorithmic game theory. We will see its application even in communication complexity. That for later. First, we would like to learn what Minimax theorem is. Okay, and it is presented in the setting of algorithmic game theory, so you will get some of the basics right for AGT. Okay, so today's idea is get some very basic information about AGT, then see what Minimax theorem is, and if time permits, we will see a proof of it. Sounds good? Okay. How many people have taken a course in algorithmic game theory? Okay. Okay. Don't worry. We need very, very basic stuff. Right? So what are games? Okay. Yeah. So what we will study, we will call them normal form game. We will abstract out most of the things. Okay. So one thing, this is going to be a one round game. Though many games which you think of as multiple round can also be framed as this one round game. Idea is n is the number of players. They are playing against each other, right? Everyone is trying to maximize their payoff. I will talk about payoff. But they are playing against each other. Number of players for today, you can safely assume n equal to 2. Or for this course, you can safely assume n equal to 2. Don't worry about rules. That was just intuition. I will describe the game mathematically, what a game means. I am going to describe now. And then we can take back your question, okay, if things are not clear. Then we have strategies. Each player I will have some set of strategies Si. Okay? Sounds good? Okay. A profile consists of one strategy per player. So think of a strategy as players move. It's a one round game. Each player has to make a move. The possible options of the move are written here. The exact description of the move is not relevant to us. This is the set of moves. Any play is a profile. That means each player has made a move. Right? So this profile P is an element of? No. The set is not the same for each player. Right? So we are looking at, right? This is a particular instance of a game. Player 1 has played whatever is P in S1, S2, so on and so forth. Okay? And strategy is not a function. Strategy is just basically, strategy is an element in this SI. Again, think of strategy as a move.
But move can be different depending on the history of the game.
Again, you are thinking of English idea of game, forget about what you know of game in your mind as in English. Look at this definition. I will give you an example and then probably you would want to call it as a move or you want to call it as a chance or whatever, but that we can debate upon. But think of strategy as a new mathematical word for you, okay? Which I'm thinking intuitively, I'm thinking of it as this is the act done by the player I in the game. It's a one round game, there is no repetitiveness, there is no dependence on others, okay? So this is the action taken by player I in that game, that is, okay?
So profile is basically describing the strategies on both sides, not just one side.
On all players.
Yeah, like, I mean, in this case, both sides.
When n equal to 2, it is describing on both sides, exactly. Thank you. And then, the most important thing, payoff. This is basically a function from, so you take any profile, it gives you a function, n numbers, which are the payoffs given to each of the party. And each player wants to optimize his or her payoff. Okay, sounds good? So, simply, okay, another way to think of it is every player, SI, think of it as a deck of cards, red, blue, green. Okay, player I can play one card from his or her deck. Depending on what cards are played, I have the payoff function. Okay, and each player is trying to optimize their payoff, right? This is the game. What we want to do with the game, I haven't told you. We will come to that. Okay, but this is a game. And again, nothing explains better than an example. So let's take an example.
So SI is a set, right?
SI is a set, yes. Sorry? P is an n tuple.
So what does it mean by maximizing a player's payoff?
Oh, their individual, see, payoff is a number here, right? So depending on this strategy, I will get an n tuple. First one is the payoff for first player. So you can think of it, okay, if you wish, you can think of it as n functions. And then first player is maximizing this, second player is maximizing, and player is maximizing this. That's also fine. Okay, so I had just combined everything and written it as r to the power n. Okay. Good. So yeah, as we say, nothing explains better than example, right? And now you will know why I made a team of 2 players in the project. Okay? So, whenever there are project partners, at the end of the project, right, this is a problem for me, and how do I solve it? I solve it in the mathematical way, right? So, there are 20 marks, let's say, assigned for the project. And if nobody complains, both get 10-10 each, which is the maximum. But suppose someone comes and says, sir, मैं तो बहुत काम किया है, दूसरा नालायक है. What am I going to do? I'm going to say, okay, complaining is costs 3 marks. Anytime you complain to me, this is going to cost you 3 marks. So if both partners complain, both are nalayak, 7 each. But in case one person complains and the other person does not complain, then I assume that the complaint is true. So then 50% of the marks of the other player will be transferred to the first player. Okay, so that means this person did not complain. This is the payoff. Should we keep this for our course?
So if 50% were transferred, so it should be 5.
3 marks for charge and then 10 marks were their total. Oh, sorry. They get 5, Yeah, yeah. So 50% of the credit. Thank you, thank you. Completely correct. So they haven't complained to 7, has nothing to do with them. They get transferred 5. Right? So first question, do you want to play this game for this course? And again, if your computer science GK is very good, this is called prisoner's dilemma. Okay? But before I describe the dilemma, does it make sense how this is a game and why this is the way you can write a game? Right? So, number of players, possible strategies. Since we have 2 players, it's always be a matrix. And then there will be 1 matrix for each payoff. I'm just writing it together here, but you can think of it as 2 matrices of 2 cross 2. Sounds good? So this is the way I can describe this game. Now it might seem like a 1-round game or anything, but if you think about it, obviously you can write rock, paper, scissors like this. This is a good exercise. How to write rock, paper, scissors? Very, very easy. You can write chess as this. You can consider all possible moves of one person, all possible moves. There will be entries where there will be a cross that, not valid or something, but still you can describe it as a big matrix. Right? So it might seem like a very, very simple game, but yes, you can describe still many things as this 2-player normal form game. Okay? But yeah, but then it is not saying anything, right? In some sense, you don't have any information about strategies inside them. I'm just taking it as a plain set. Probably there is a relation between them and things like that. All those I'm losing out. So it's not a great description, but it captures a lot of games. Sounds good? Okay. So now, what do you think players should do? Exactly, right? So if you look at this matrix, let's say, if I'm looking at the first player, right? First player, irrespective of whether the second player complains or do not complain, he is better off complaining, right? So in that case, selfish reasoning suggests complain. But global happiness and actually your personal happiness is also maximized if you do not complain. This kind of tells you the importance of trust, which we lack in Indian society, but this exemplifies that fact, right? Trust helps. Though, since you're looking at it mathematically, this is not our concern. Okay? So this is called prisoner's dilemma because for a prisoner, if both of them don't complain, they get the best. But then what it will turn out is, if they're just looking out for themselves, they're going to complain and both get the worst possible answer. Okay? But getting back from prisoner's dilemma, the strategy of both complaining is actually what we call Nash equilibrium. What do I mean by that? No player has incentive to switch the strategy. Okay, what does it mean? If I am here and I keep fixing my strategy, other person cannot get a better payoff. I can't lose. Other person does whatever, this is going to be my best answer. Similarly, for the other side. So Nash equilibrium is every player, no player wants to switch. Because if they don't switch, other player does whatever, they will stay at the optimum. Okay? So this is called a Nash equilibrium, and here, this is the Nash equilibrium. Does Nash equilibrium always exist? What do you think? Yes, no? Yeah, so you can actually construct easy games where you don't have Nash equilibrium, sorry, I should say. So this could be a payoff. This is, in some sense, you are saying that, there is, in this case, person will give you 7 rupees to the other player, in this case 9 rupees to the other player. You can think of it as, these are called zero-sum games. Because one player's loss is another player's gain or something. But so in this case, it is very easy, but even in this case, you can easily find this payoff matrices where none of the strategy is a Nash equilibrium. Because at least for one player, it makes sense to switch. Okay, so I will just change this and I will call it a deterministic Nash equilibrium. And you will get the reason of why I am doing this, and now it's clear that deterministic any need not exist. Okay,